All right, so this slide's meant to quickly talk through why is Microsoft at NANOG talking about open subsea cables. So if you're running a Microsoft service, you're going to run it on the Microsoft WAN. So we have our own backbone, switches, routers, fiber optic cable, connecting data centers, connecting regions throughout the world. So our goal, as close as possible to you, the customer, more often than not a commercial customer, will suck the bits onto the Microsoft WAN and run them over our network. We do it for a number of reasons. Cost, a big reason, but most important reason is availability. We get end-to-end control over the network, the supply chain, etc., and we feel we can deliver capacity quickly, more quickly than going through third parties, and in a more controlled manner. So we get that control. Cloud's hot right now. Exponential organic demand. I think throughout the week you've probably heard that, and it's real. When I say organic demand, it's actually cloud service adoption. More and more people going to the cloud is causing exponential capacity demand. That's hitting the WAN, and that requires a very creative transoceanic strategy, and that's what we're here to talk about. So the Azure blog, published recently, showed the scale of the Azure WAN, and here it is again. Very high level. It's not all owned. Majority of it is owned. There's some lease, some partnerships. One thing I notice when I look at it is a lot of subsea cables, a lot of blue lines running through the water, a lot of cables. And we'll talk about why there's so many later on. What is a subsea cable? What are the building blocks? When I look at a subsea cable, I see essentially two pieces, two things that we worry about a little bit separately. A dry plant and a wet plant. So the dry plant is the point of presence, the data centers, and shown here power feed equipment. Those sit in things called cable landing stations or data center buildings. At the cable landing station, we switch from dry plant to wet plant, and that's where we go underwater. When you go underwater, you've got subsea cable. Shown here are three different types of cable. The thicker one on the left is double armored, typically put in shallow water. The armor is there to stop fishermen from hooking it and breaking it. Once you go further underwater, about 60 kilometers out, you hit your first repeater. So the undersea repeaters amplify the photons. So there's actually amplifiers under the water. And you keep going, you can get branching units about every 60 kilometers, more repeaters. By the time you cross an ocean, anywhere between 100 to 250 repeaters under the water. And of course, here's shown a boat laying it all, laying the cable. Some pictures of what this looks like in real life. You see the subsea landing station. The landing station, a building. Building itself is not that big. That's important to keep in mind when we talk about how to build a good optical and switching architecture. So you don't have a lot of space in the landing station. Beside the landing station are, in this picture, two big generators. If you're ultra paranoid about availability, you have backup power. So you're seeing two generators just about as big as the building to power all this. There's a picture of a shore burial and also an undersea plow. So when you're laying those components we just talked about, the cable, double armored cable, single armored or no armored cable, and the repeaters, there's actually a plow at the bottom of the ocean that buries it. And there's a guy in a boat driving it like a video game and burying the cable, burying the cable, burying the cable. So, pointing all of this out to show it's a feat of modern engineering. It's very labor intensive. It looks awful expensive, right? Okay, we'll talk about the cable for a second. And this stuff it's really cool. So around the outside of the cable, you're seeing here steel tubes. The steel tubes they're not there for pressure, they're there for armor. I mean, in this case, this is a double armored cable. So you see 2 layers of steel tubes on the outside of the cable. Inside the 2 layers of steel tubes, you get to kind of the meat of the cable, the telecom network. There is a power, a powering element. It's copper. And there's a lot of science that goes into it. How thick the copper is, it directly relates to how much power you put on the cable, which directly relates to how big your power feed needs to be, which indirectly leads you to how much capacity you can put on one of these cables. So you've got the power in there, you've got an insulator, and in the middle, it's just very tiny little middle, are the optical fibers that run through. Typical cable can run between 8 and 12 fiber pairs. Put that in perspective, typical terrestrial buried cable is somewhere near 100, some of them near 200 pairs of fiber optic inside the cable. So you get about an order of magnitude less fiber pairs in a subsea cable. So a subsea cable about an order of magnitude lower capacity than a terrestrial cable. The power feed equipment is really cool. So you have this long cable, imagine 12,000 kilometers across the ocean. And all you have is stuff on the ends. That's what you power it with. In this example, I've shown a 14 kilovolt PFE. So what you do is you set your PFE +7 on one side, -7 on the other side. And somewhere in the middle, there's a virtual ground. It hits 0. And the 14 kilovolts runs across the copper, I call it a few milliamps, and it powers all of the active components of the cable. Remember, every 60 kilometers to 80 kilometers, we are amplifying the light. So we send light on the end, we amplify it, and we get the packets from one side to the other. So the power feed equipment creates this virtual ground. One of the most common failures of a subsea cable is a tear in the sheath. So outside of the armor here, there's a black tarry looking thing that keeps the water out. And over time, the cable chafes with current, a little bit of water gets in, and when the water touches that copper, it immediately changes the ground, right? Because the sea is a great ground. So in this example, you can see the bottom one, if I'm a few hundred kilometers off the coast and a little bit of water gets into the cable, the PFE actually changes and the ground moves, and one side in this example goes up to 12 kilovolts, the other side changes to -2, and I've got a real ground, a sea ground that has just been created. It's really important because fixing a cable requires calling a boat. The boat comes out, fishes it up, takes it apart, and puts it back together. If it's unscheduled, it can take weeks, sometimes a month for that boat to get out there. So by having the power feed equipment have the capability to change the ground if the cable gets compromised is one of the reasons that these things are somewhat available. They're somewhat, they have a good uptime, good availability. Now you can only handle one of these. If 2 of these happen, you're toast. So when they do happen, there's all kinds of alarms and you get the boat out as quick as possible. But that's, in a nutshell, how the cable's powered. So you want to design the cable to do what we call single end feeding. You want it to have, if it's too long, you can't do this. If your power feed equipment doesn't have enough voltage, you can't do this. And if you put too many active components in the cable, like repeaters, you get better performance, but you might not be able to do this. So all these trade-offs. The repeaters, you'll hear me say it a lot because these are super cool as well. There are these big titanium tubes, and we brought one into our lab, and many hundreds of kilograms weighed. We had to get a special crane, take windows out to get it in. So a subsea repeater is made to go down to 5 to 8 kilometers of depth. Inside of it are just amplifiers, erbium doped fiber amplifiers. You see them in any terrestrial system by the hundreds. So the technology inside is no different than what you see in a terrestrial system. It's controlled in a little bit of a different way. It's run in a little bit of a different way, but fundamentally the same technology. The cool part is they put it in this titanium tube that you can sink down to 8 kilometers of depth, and it can handle that pressure. And run reliably for 25 years. Now the size of these repeaters also limits how much fiber you can put in the cable, which limits how much capacity you can put in the cable. You can imagine everything I just described doesn't come for free. So I have a note on the bottom here, $3 signs, which means expensive. These are very, very expensive. One of the most costly pieces of a subsea cable. And of course, we pay a lot for them, so you get to put your name on them. So if you have a cable that you own, they let you scribe your name on the side. So 25 years from now, if someone finds one with their name on it. Reliability. One of the biggest problems with relying on subsea capacity is reliability. It's an interesting article from mentalfloss.com. Number 2 most interesting fact, I don't remember the number 1, but I imagine it was good. Sharks are trying to eat the internet. This is real. The powering of that cable we just talked about, imagine you're sending 14 kilovolts across the ocean. It's a little bit of an electromagnetic field that happens. These things are kind of like giant antennas, and it makes the sharks angry, so sharks do tend to bite them. It is a cause of cable cuts. Now, the most common cause of cable cuts is simple chafing from ocean currents. You have rocks on the bottom, the plow didn't bury it quite deep enough, probably because we were trying to save some time. And the ocean currents over 10 years chafe that cable back and forth. I take a shunt fault, or even worse, a clean cut. If you take a clean cut in deep water, for example, the North Atlantic, it could be a month before someone goes out there and fixes it. A month. Imagine losing that connection for a month. So connecting 2 regions, take US to Europe, for example. You don't just run a subsea cable and say you're done. And of course, a lot of people ask, why don't you use satellites? And there's a lot of latency in satellites. If you had to wait 8 seconds for your SharePoint site to load, you might be a little upset. So we use the subsea cables. So you run these subsea cables. You can't just have your one. If I want to get 1 bit from here to Japan, I can't just have 1. It turns out you do the math, and best case scenario, you need 3. If you want to 1 bit from here to Japan with any kind of reliability where you can stand in front of your customers and say, we'll get you the bits there, you need 3 cables. So there's a tripling. Now, if you build it wrong, you're going to need more than 3. And these cables are very expensive, hundreds of millions of dollars. So it's expensive business. So 3 or more cables to get a bit across. Which leads me to the problem statement. We talked about cables are incredibly cool. They do all kinds of cool stuff. Along with that is a price tag. They're very expensive. They have a very long lead time. If I want to add a bit between here and Japan and there's no more subsea capacity, we'll kick the project off 3 to 5 years down the road, the boats are laying the cable. So they have a very long lead time. A lot of the time is in surveys, marine surveys, permitting, especially here, making sure you don't make the orcas angry as you run through the Puget Sound. So a lot of time goes into the permitting and planning. So before you can even start to lay the cable, you have to get all that in order. It's a limited resource because they're expensive, because there's only so many companies that make them. There's a supply chain bottleneck. And you only get about 20 terabits per fiber pair. 20 terabits per fiber pair times 6, 8, 10 fiber pairs. It's not a lot of terabits in comparison to a terrestrial backbone. A terrestrial backbone can run something like 24 terabits of fiber pair on 100 fiber pairs. The subsea bottlenecks that into something like 8. So it's a very limited resource in terms of how many there are to choose from. And if you need a lot of capacity, you're out of luck. You might need more than those 3 cables we talked about. And then they have a very low availability compared to a terrestrial asset. Your subsea cable, you expect it to break. You expect it to take a month to fix when it breaks. So over the lifetime of the cable, somewhere between 1 to 2 nines of availability. So you need a lot of redundancy to build a 5 nines cloud network. So when you do invest in a subsea cable, you have to be really smart about the choices you make. You have to be creative about where it goes. If you're running a cloud network, you don't want to run New York, London, like the stock traders have their 5 cables to do. You need more diversity. You want to run somewhere different. So diversity is the key, not capacity, not necessarily topology, it's diversity. And once you do invest in that asset, you want to make sure you make the right choices around the asset to enable it to give you the absolute most efficiency. We'll talk about SLTE. So earlier we mentioned there's a wet plant and a dry plant. So we talked about the cable. It's got the cool power feed equipment, incredibly cool repeaters, very expensive. In the cable landing station, we have SLTE, submarine line terminating equipment. This is the optical transponders, transceivers, muxponders, use your favorite term, that light the cable. Using modern equipment is the easiest way to get efficiency out of these cables. I have a table here showing one of the common tricks used, modulation format. Modulation format, you can see in the table, QPSK 8 QAM, 16 QAM. We don't have time to go into exactly what those mean, but they convert to capacity. So if I can run QPSK, I can do 12 terabits, 8 QAM, 18 terabits, 16 QAM, 24 terabits. And the fixed cost is the same. So essentially, the higher my modulation format, I've got this fixed cost of my asset. I get more bits out of it. So if I get more bits out of it by using this trick, I essentially reduce my cost per bit, which is a good thing. A lot of technology advances in submarine cables have been here. The cable itself fundamentally hasn't changed 15 to 20 years. Things got a little wider in terms of bandwidth. The designs have gotten a little more cost-effective. They're not over-engineered, but the cable technology hasn't changed in a long time. The terminal equipment, the SLTE, has changed really rapidly to get the most out of that cable. A subsea cable is expected to last you 25 years. So when you put it at the bottom of the ocean, you've got 25 years of lifetime. The SLTE, follows Moore's law. Every 3 to 5 years, what this can do doubles. So you want to design your cable to enable Moore's law to do its work on the ends and get more and more efficiency out of that cable as it ages out. So you've got this 25-year static thing, and every 3 to 5 years, you're cycling what's on the ends to get the most out of it. Now, to do that, there's 3 different ways you can buy a cable. You can do a closed system. You can say, I don't have the expertise to engineer this, so I'm going to get a turnkey solution. You're going to get the SLTE, the cable all together. Upside is it's easy. The downside is, we'll get into that, it's a bit ugly. The middle is an upgradable system. You start turnkey, and then you do some surgery, not brain surgery, but complex surgery to extract the turnkey SLTE and put somebody else's in down the road. It's a little more flexible than a closed system, but has its downsides too. And then what ourselves and the other cloud providers seem to be pushing and requiring are open cable system. And very small differences between the 3 that have very large impact on the efficiency of the cable over 25 years. So we'll ignore the turnkey. The upgradable system starts its life as a turnkey and then works its way into a quasi-open system. In an upgradable system, you've bought it as a turnkey. When you buy a turnkey system, the measure of whether or not that cable is good. So remember this thing that costs us hundreds of millions of dollars, and we've sunk it at the bottom of the ocean. If you want to know how well it's performing in this model, you ask the SLTE how fast it can go. Essentially how much capacity you can put on the cable, modulation format that we talked about a few slides back. If you think about it, that's like saying because my car can drive 70 miles an hour, there's nothing wrong with it. It's the wrong way to measure quality. You're abstracting the expensive thing behind the thing that you want to recycle. So you lose visibility of what's actually happening on the cable. And I've seen this firsthand on over 30 cases over the last 10 years, where the cable itself has a systemic problem. It's degrading. Your tire pressure is getting low, your engine is failing, but the car still goes 70 miles an hour, right? And I don't know if you're like me, you've owned a car that had no business going 70 miles an hour, but you did it anyways, the same thing. The SLTE was saying, I can still hang on, but something was getting worse. So over time, the cable has degraded, and then you want to put the newest, latest, and greatest technology on it, and you've let your $100+ million asset degrade because you did not have visibility of what was going on at the bottom of the ocean. So how do we solve it? How do we solve that? Got a picture of us doing a subsea cable turnup. We purchased one of these closed systems. We did 2 months of planning to surgically remove the turnkey, SLTE, and then we sent a rolling lab. It was actually 3 crates, over 500 kilograms a crate, a rolling lab out to site, and we spent 4 people, 2 weeks, 16-hour days, a lot of coffee, and we extracted the current state of affairs from the cable. We did a lot of measurements. Even that is not the best way to do it, but at least it's an order of magnitude better than just asking the SLTE, hey, how fast can you go today? So you send a rolling lab out. If you want to scale fast, if you want to get capacity out there fast, you can't do this, right? You need a better approach. You can't roll a lab and 6 experts for 2 weeks every time you want to add a terabit. It's just not going to scale. So what have we done? We've opened the cables up. So any new cable that we purchase, any new cable where we're a consortium, any new cable where we lease even, we ask it to be an open cable. The difference here, you can see this clear separation between SLT and the cable. And the gray boxes, I should have probably used a more interesting color because these do really interesting things. We've invested in technology to measure the cable with more precision. So these gray boxes now can go query the cable span by span and ask it how it's doing today. So we essentially created check engine lights and all the other fun lights your dashboards have. One of the really cool advancements is a line monitoring system, or a coherent or correlated OTDR. So we send a signal from the shore, and the amplifiers under the water have a return path built into them that's out of the band of where we send our bits. And over time, and a lot of math, we can actually extract a span-by-span OTDR. So in real time, we run in-service OTDRs on the cable, and we create this visibility. Every span, I understand what's happening. And then we stick an optical spectrum analyzer on the ends, and we measure physical properties of the cable, like OSNR, like power tilt. So the actual figures of merit for how well the cable is performing, how healthy the cable is directly. And then we alarm and alert on those. It's no longer we're asking the SLT how fast it can go. We actually have a completely new set of measures directly related to this asset at the bottom of the ocean, and we alarm and alert on those directly. Simple change, huge impact. Now I know in real time the health of that expensive asset. This manifests itself in some interesting ways. Improved availability is the most interesting. If you have this, you can, in near real time, see something degrading. So, we talked about the sheath of the cable degrading. You probably get forewarning, right? Over time, you build enough intelligence to see that process happening. It's not binary, it's analog. Not going to go into detail here. This is a little detail on how you do it. Power versus lambda picture, I just wanted to point out, the cable itself is analog. It's delivering an analog signal. So we've actually built the expertise on the end to evaluate that analog signal. A little more expensive, but compared to the price of the cable, it's a good investment. All right, so we talked about the cable, the SLTE, and what we do in the SLTE. Let's talk a bit about, now we got to get into the data centers. Generally don't build data centers on a beach, a lot of good reasons. tidal waves probably being one of them, floods, hurricanes, et cetera. Generally, you build the data centers inland somewhere much more reliable. The old school mentality is, well, I've got my cable, I want to get the bits across as cheap as possible. I'm going to put my transponders and switches in the data centers and just run everything like one path. Now it turns out if you make a little change in your landing station, you put a packet switch in here, and this packet switch is a commodity layer 2, layer 3 switch you can buy from a number of vendors. True blue packet switch, and you stick it in your landing station, and you have diverse backhauls to your data centers. So you run 2 fiber paths on land. Your availability improves significantly. And this is the difference between needing 3 cables or 4. In some cases, the difference between needing 2 cables or 3. So if you can invest a little bit in your landing station, and the costs of these aren't very high, you can save a cable. And the cost of a cable is very high. So once you're in the landing station, put a packet switch in. And we call these packet switch SLTEs, or packet switch CLS. So any new cable, we like to see some sort of packet switching in the landing station, and we go diverse to the data centers. It's a very different mentality than a true carrier. A true carrier would probably run it what we call pop to pop, where they would run it packet switch to packet switch in the endpoint, and their end-to-end path is susceptible to cuts on the terrestrial and subsea. All right. So we're back in the data centers. How do we run these things? I think open line systems on the terrestrial side have been very well published, talked about for the last 5 to 10 years. And we're no different. We believe strongly the same reasons we just discussed in subsea. We want to cycle the terminal equipment more often than the line. All of our terrestrial systems going forward are open line systems with a Microsoft SDN controller. So we have our own network management system that we built. And we want the subsea cable to plug into this. Why do we want the subsea cable to plug into it? I mean, subsea cables are incredibly cool. From an optical guy's perspective, it doesn't get more cool than that. But in terms of number of bits you run over a subsea cable, they're limited resource, they're expensive. So you're going to tune all your software stacks, all your replication patterns to not use it unless it absolutely has to. So all of your data center replication, you're going to try to keep it on a continent unless you absolutely cannot. The majority of cloud traffic is this kind of replication, storage replication. So you can see the metro, we have a lot of capacity. Long haul, we have a lot of capacity, not nearly as much as the metro. The amount of subsea bits we run, it's a lot in comparison, I think, to a traditional carrier, but in comparison to what we run in the metro and the long haul, it's very small. So we architect our tooling for the majority use case, the metro and long haul, and we'd like to fit subsea into that. Now, of course, there's custom bits, but the building blocks are the same. It's an optical system. So we really focus on the scale, the large applications, and the open cable plugging into it. Last slide here, Maria cable. Maria cable is a well-published cable that we partnered with Facebook on. We built it across the Atlantic. I'm showing this, not to brag, although it is pretty neat. This is the perfect example of why you might own versus just leasing. You see the Maria cable. It runs from Virginia Beach to Bilbao, Spain. Virginia is where data centers are. It's the first cable to land that far south on the North American side. A lot of the cables between US and Europe run as high north as possible, New York to London, to get that high speed, low latency path. When you're running a cloud network, you don't necessarily need that. You want your availability. You want your 5 nines. So we built a completely diverse path, and then we made it completely open packet switch landing stations. So Maria is a great example of an ownership on the cloud. So going forward, when you're looking at what ourselves and the other cloud providers are doing in subsea space, you're going to see a lot of wacky landing points. We're going to try and get these in diverse places where cables have never been, and that's where I see the investment going. Thanks.
Great presentation. Thank you. Matt Petak from Yahoo here. So you took out the somewhat closed proprietary SLTE system, which wasn't giving you visibility into the subsea fiber, and you replaced it with your own cobbled together homegrown system that replaces the SLTE and tells you what's going on with the fiber. That's basically just kind of swapping out one smart box for a different smart box, isn't it? Can you clarify why you felt that you couldn't just have the SLTE itself give you more visibility directly rather than replacing one box with another?
Yeah, it's a good question. The SLTE fundamentally abstracts the performance behind something like prefect bit error rate. Prefect bit error rate is not a direct measure of the quality of the system. There's a lot of things at work. So, for example, you could have a bad prefect bit error rate because of high launch power. And high launch power might be a sign of a perfectly working cable, in fact, a cable that's working better than you thought. So the SLTE abstracts the performance behind this number that has no direct relation to how it's performing. So when you're saying the SLTE gave us what you needed, the SLTE gave you prefect bit error rate. And from that, you had to guess whether or not the cable was the cause of the problem or something else was the cause of the problem. So we still use the prefect bit error rate. Still use it. It's still a valid measure. It helps us understand the nonlinear performance of the cable. But the linear performance of the cable, the thing you're paying for, the repeaters, the fiber effective area, things like that, that is directly related to OSNR, optical signal noise ratio, and tilt, and power. So what we're saying is we've added monitoring for OSNR, tilt, and power directly, and we alert and alarm on that directly. Still have prefect bit error rate, but now I know if the prefect bit error rate is bad, I can look at this other thing and say it's the cable. Another reason you do it, I've got something not performing, I want to fix it as soon as possible, immediately I know who to call. I know if it's the cable or something inside.
But you didn't go to the vendor and say, hey, we'd like to have you add these capabilities in and expose the results to us so that you didn't have to build a completely new box for it. Yeah,
and then, you're right. So the alternate approach is you go to the SLT vendor and you say, do this for me, which is valid. If you want two vendors, now you have two different solutions to integrate into your SDN controller. 3 years down the road, the vendor you picked might suck. Be frank, might have went the wrong direction for you. You want to replace them. Now you've got the burden of doing this again. Why not just put the monitoring in day one and run it for 25 years and then use that same thing on every single subsea cable you own? Remember, these subsea cables, 8 fiber pairs, about 10 new ones going in a year. Just put a lot of these out there day one, let them run for 25 years and don't worry about it. That's our philosophy. How do you onboard and turn these things over as quick as possible? And I see letting the vendor do it is a barrier to doing this quickly, eventually. Day one, same. 5 years down the road, when I've got 4 different monitoring systems doing things a little differently, I see problems there.
Makes sense. All right, thank you.
Hi, Eric Kunke with Knoll Communications. My question is regarding the use of a cable landing station as a terrestrial interconnection point. A couple of years ago, I did some work related to the ACE cable landing station in Freetown, Sierra Leone, in West Africa. And the interesting thing I noticed about landing stations in West Africa, and particularly all of the recently installed systems, is that they are the most significant reliable piece of telecom infrastructure anywhere in a given nation state. So ISPs and network operators and mobile phone operators, whoever is an operator in Liberia or Sierra Leone or a location like that, those cable landing stations have become the de facto interconnection point, similar to a 60 Hudson or to a 1 Wilshire.
Yep.
And what do you see the role of, on the terrestrial side, for interconnection between ISPs and co-location and hosting of a landing station in a developing nation environment, considering that ordinarily people don't build colos on the beach, but that's what these have kind of become.
Yeah, you're right. I think I overgeneralized. There are parts of the world, and particularly developing countries, where the terrestrial challenges are very, very difficult. For example, Brazil. We experience a cable cut a day on the terrestrial side, subsea much more stable. So countries like that, you're correct. Generally, we can pull the switching closer to the ocean. Now, still, I don't think the right thing to do is put a data center potentially that close to the ocean. You want power diversity. You want good fault segregation. You just want an ultra-available building in an ultra-available place. So what we do in that case, instead of just doing a simple packet switch landing station, we would probably do a full, what we call a gateway. And we would turn the landing station into a full gateway. You need to know that ahead of time because that's a lot of space and power. That's typically not there in landing stations. But it is a good point. Going diverse, how you do it, it does change depending on what continent you land on. Yeah. Thanks.